Hi, good evening, my lovely year 11s. I'm so sorry. I should have recorded this in class, but turns out I only realized midway that there were three students who were not in the class and they're going to miss out on the start of a new chapter, and I don't want that. So what I've done here is I'm going to quickly recap what we did in class. These are the notes from the class, but if I just uploaded the notes, I do understand that you wouldn't be able to decipher what all of this means. And I really don't want you to be stuck in that situation. So I'll quickly go through it. It should take me what 5 minutes or maybe 7 minutes to go through it as a whole. Uh, so what we started off today was we talked about molecules, and we talked about the fact that all molecules have a shape, and the shape of the and the shapes of the molecules that we the big shapes, the broad shapes, or the five main shapes that we know about are linear, trigonal, planar. It's here it says triangular planar, and in Lucarelli it says triangular planar as well, but it is also known by the word by the name trigonal planar, pyramidal, and bent. So I will be mainly focusing on these five shapes throughout this chapter. So my first question that I asked in class was, how do you determine the shapes of the molecules? Why is it important to know the shapes in the very first place? Well, the reason that we determine the shapes of the molecules is that knowing the shapes of the molecules helps us determine how molecules uh, would collide in a chemical reaction, whether it helps us determine whether collision would be successful. Now, that's not the only factor, there are other factors, but this is one of the factors. A shape of a molecule will determine whether the collision is successful, and if the collision is successful, that basically means that a reaction could occur. And chemistry is all about reactions. Um, so that is the basis of doing of learning about molecular shapes. But molecular shapes could explain the chemical reactions. They could explain physical properties. Um, so the next question that we need to ask ourselves is what? How do we determine the molecular shapes? Well, we determine the molecular shapes by a theory called the Vesper theory, uh, which stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Now, throughout the rest of the lesson, I'll just call it Vesper. It's a mouthful, calling out saying VSEP, valence shell electron pair theory. Okay, what I did after this was really quickly, I asked the students to uh, take 14 minutes, 2 minutes for each question here, and I asked them to draw Lewis structures. And Alisa, Brittany, and Paula, if you're wondering why I asked them to draw Lewis structures, it was mainly because it helps us determine the shape of the molecule, and you'll see why. There are some rules which uh, which you can use upon those Lewis dot structures to determine the shapes of the molecules. So these are the seven molecules that I asked to ask students to draw Lewis dot structures of. Now, if you are struggling, if you don't remember how to do Lewis dot structures, you can go to covalent bonding. Go to bonding in your Euclid textbook and look up the 3 or 4 rules which were there, which helped you draw Lewis dot structures. When you have done that, and you have drawn all these structures, then you could just resume the video. So just pause this video, all three of you, go get your textbook, quickly look up how do we write Lewis dot structures, and then once you have drawn them, then only resume the video. Okay, so if you have drawn the structures, you'll find that the first one for carbon dioxide, the structure looks like this. You have these two lone pairs on oxygen, on each oxygen. You have a carbon, and the carbon is double bonded to the two oxygens. Now, first thing that you need to know is the shape of the molecule is dependent on the central atom, the atom right in the middle. The central atom will decide the shape of the molecule. And if you have one or two groups of electrons, so one or two groups of electrons around that central atom, then the shape of that molecule would be linear. And that is kind of expected. Think about it. If you have two pairs of electrons on a carbon atom or around a carbon atom, how would they want to arrange themselves so that they have the so that they are as far apart from each other? The electrons would want to be as far apart from each other as possible. So how would they want to arrange themselves around a carbon atom so that they're as far apart from each other? Now, if you said diametrically opposite, that's right, because they'd be as far as possible around that carbon atom. And so that's why I wrote first the electrons need to repel each other, and second, they would want to be as far as possible from each other. And that gives us a linear arrangement which has a 180-degree angle. It's a linear molecule. Now, we also talked about trigonal planar. Now, if you drew the third structure, the structure would have looked like this. Now, have a look really quickly. How many pairs of electrons are there surrounding the carbon? So, there's one pair of electron in the bond between carbon and hydrogen, another pair of electron between a bond between carbon and hydrogen, and then another pair, another two pairs in the bond between carbon and oxygen. So, think of it, there are three groups. Remember that the double bond will although there are four electrons there, we will just call them, for our sake, we'll just call it one group because they're together. We'll just call it one group of electrons. This is the second group of electrons and third group of electrons. So in total, you have three pairs of electrons. How would three pairs of electrons be arranged around a carbon atom, or how would they arrange themselves so that it leads to the maximum repulsion? Turns out that's a trigonal planar structure. That means more of a triangle, which is 60 degrees. So the carbon and oxygen and carbon and hydrogen are 60 degrees apart from each other. Now, we also talked about tetrahedral structures. For instance, methane. If you would have drawn the structure for methane, you'd find that there are four pairs, four groups of electrons. One group, this group, this group, this third group, and then one more. That gives rise to four groups of electrons, and four groups of electrons would repel each other to form a tetrahedron or tetrahedral structure. Now, Lisa, Brittany, and Paula, I'd suggest that you quickly go to Google and look up what a tetrahedral structure looks like, and even look at linear structures, trigonal planar. Just find images because they are three-dimensional structures, and I can't draw them here. Your book has a few pictures as well, but they're not as good as the ones that are on the internet. We also talked about, this was the last thing that we talked about, a bent structure. Now, water exhibits what we call a bent structure. Now, if you look at the groups of electrons around this oxygen, the central atom of water, you have one group, two group, three groups, four groups. So a pair of electrons here, a pair of electrons here, a pair of electrons here, and a pair of electrons here. That makes it four pairs of electrons. However, it does not exhibit, well, cutting down on that. So what would you expect it to exhibit? You would expect it to exhibit a tetrahedral structure. There are four pairs of electrons. This should be no different than CH4. However, it is. It is very different. The in a tetrahedron, a tetrahedral structure, the angles are 109.5 degrees. However, in a bent structure, the angle is 104.5 degrees. How do you explain the difference? How do you explain that it went from 109.5 degrees to 104.5 degrees? Now you can explain it because it has lone pair of electrons. These lone pair of electrons actually repel each other more than uh, the bond pair of electrons do. In other words, the repulsion between these bonds, these two bonds that I am circling, is lesser than the repulsion between these two um, lone pair of electrons. In fact, the repulsion between lone pair and lone pair is greater than the repulsion between lone pair and bond pair. That means between this pair of electron and this pair of electron is greater than a bond pair repulsion. That means between these two. And that is why that repulsion between lone pair and bond pair and lone pair pushes the bonds inwards even further, and that decreases the angle from 109.5 to 104.5. The last thing that I asked the students to do was to go through the rules on page 123 of ukulele, and that was the end of the lesson. So I hope this helps. I don't want you girls to fall behind. Take care. I hope you're doing well.